Our world is changing.
Engineering is changing.
Society is changing.
We are changing.
We're here to inspire,
Inform,
influence,
and change perceptions.
Demonstrating how important engineers and technicians are in our lives.
Championing achievements, helping to create new technologies that enable us to thrive,
and inspiring future generations to make a difference.
Together, we discover new concepts by turning theory into practice.
create solutions to society's biggest challenges,
Share knowledge and expertise through our networks.
grow by developing new skills and capabilities,
evolve and adapt for the future.
We are the IET.
Together, we are engineering a better world.
Our world is changing.
Engineering is changing.
Society is changing.
we are changing.
we're here to inspire,
Inform,
Influence,
And change perceptions.
Demonstrating how important engineers and technicians are in our lives.
championing achievements, helping to create new technologies that enable us to thrive,
and inspiring future generations to make a difference.
Together, we discover new concepts by turning theory into practice.
create solutions to society's biggest challenges,
Share knowledge and expertise through our networks.
grow by developing new skills and capabilities,
Evolve and adapt for the future.
We are the IET.
Together, we are engineering a better world.
Our world
Welcome to the live webinar on CFD by Torsion IET-NITK. In this webinar, we are going to learn how to run and understand the CFD simulation. So the topics covered in this webinar will be as follows. So yeah, first one, the very first one is the general terminology of theory, and then steps to achieve our CFD simulation. Then Navier-stokes equation discretisation, and turbulence modeling and on Ansys. Yeah, and speakers of this live webinar are Sagar and Vishwa Mohan Tiwari. So Sagar will be taking the introduction part of the webinar, and Vishwamohan will be introducing the numericals and calculations, and will be teaching you the simulation of the software. So yeah, I'll ask Sagar to take forward the stage.
So yeah, thanks Nitish, and yeah, hi everyone. I am Sagar, third year mechanical student from National Institute of Technology, Karnataka. So today we are going to cover some few topics from fluid dynamics, and mostly I will cover the some interesting application of fluid dynamics. And later on, Vishwa will show you the live demo on Ansys plant, like how you can simulate this problem in Ansys plant. So let's start with some interesting questions. Like you can see the image, like birds are flying v shape, like how beautiful it is. So yeah, thanks Nitish, and yeah, hi everyone. I am Sagar, third year mechanical student from National Institute of Technology, Karnataka. So today we are going to cover some few topics from fluid dynamics, and mostly I will cover the some interesting application of fluid dynamics. And later on, Vishwa will show you the live demo on Ansys plant, like how you can simulate this problem in Ansys plant. So let's start with some interesting questions. Like you can see the image, like birds are flying v shape, like how beautiful it is. Like most of the birds fly in v shape, but why? What is the reason behind this? You know, after knowing the physics behind this, I came to know that birds are more intelligent in physics than me. And the next question is, next slide please. Yeah, why golf ball has dimples? Why they are not using the smooth ball? And the next question is, like, why most of the cyclists are very close enough in a cyclist pattern? So these are the some interesting questions. We are not aware of the what is the reason behind this, but we will try to cover the reason behind in this meet. So yeah, next slide please. So yeah, before that, like you are getting a question like what is aerodynamic effect and what aerodynamic effect can cause a maximum. So I want to show a small clip which will that will tell you like when what an aerodynamic effect can cause. Yeah, can you play the small clip? So this is the clip. So here we are dropping a basketball in the two case. The first case is we are dropping the ball without any spinning the ball. So you can see that this is the first case. There is a no huge change in the trajectory of the ball. It's just let down the ball where we want to drop. But in the second case, we are giving a backspin to the ball. So now you can see there is a huge difference in the trajectory of the ball. It looks amazing, right? Because giving a just backspin can cause a huge difference in the trajectory of the ball. So this is the physics, like what aerodynamic effect can cause. So yeah, what is the reason behind this? Yeah, guess and let us know the answer in the chat box. And later on we will come to know the reason behind this. Yeah, next slide please. So yeah, move on to the next. I'll start with my experience, like how my area of interest started in this field of fluid dynamics, and later on we will see the reason behind this. So yeah, first of all, I want to say that I am a sports person, and I used to play many games like cricket, volleyball, and football. So nowadays I used to play volleyball, and this is the game which creates my interest in the field of aerodynamics. Yeah, next slide please. I don't know like how many of you know some rules of volleyball, but I will try my best to make you understand what I want to say related to aerodynamics in this game. So yeah, there are mainly three types of serve in volleyball. The first one you can see in the image is normal serve. In this case, we are just simply standing near the outline boundary of our court and hit the ball in such a way that it just cross over the net and reach to the opponent team. The pros in this case is like we are saving our energy because we are just standing, and the accuracy is very high in this case because we are not jumping. So accuracy is high because ball is in our control. And the con is in this case is that we are not creating any difficulty for the opponent. This point is very important because we are focusing on this because everyone wants to win. So if we wants to win, we have to create some difficulty for the opponent to take the pass. So yeah, we'll try like how we can create the difficulty in next slides. Yeah, next slide please. So this is the second case, jump and serve. In jump and serve, we have to hit the ball in the middle of the air with the help of long jump, and we need to transfer our momentum to the ball. So the pros in this case is we are creating the difficulty what we need, but the cons in this case is like accuracy is low compared to the first case. Accuracy is low because it's very difficult for us to hit the ball in a proper time and in a proper contact, because ball is in the air and we are also in the air, so it's very difficult. And the second con is like we are losing the energy because we are jumping by itself, so it's very difficult for us to continue with the same pattern as we start in the starting, so our efficiency decreases with the time. So the next case is the third type is float serve. Float serve is which us the float serve is the one which compel us to understand the physics behind the aerodynamic effect. So yeah, the pros in this case is saving the energy. We are saving the energy in this case because we are just standing and hitting the ball. And the second one is like accuracy is also high in this case because ball is in our control, so accuracy is also high. The third, the most important one is creating difficulty for the opponent team to take pass. Yeah, the most important we are focusing is creating the difficulty for the opponent, and in this case we are doing that. And the con is in this case we can say is this is not con, but this is a like it's not everyone's cup of tea to do this task because it's require a lot of practice and it's very hard to do this. So yeah, next please. Yeah, this is the float sir, you can see small animation how the trajectory of the ball is changing with respect to the time. So yeah, this is the ball, this is the float serve. So it's very difficult for the opponent to understand the trajectory of the ball. So now we are creating the difficulty for the opponent to take the pass. So this is our mission. So we are doing this. So what is the reason behind this? Yeah, we will see that. Next slide. So yeah, science behind this all, like we have seen so many interesting applications. So what is the reason behind this? So there is an important term called Magnus effect. The Magnus force is named after the German physicist Heinrich Gustav Magnus, who described the effect in 1852 when he was trying to observe the trajectory of cannonball when propagated through air. So basically the Magnus effect is an observed phenomena that is commonly associated with a spinning object moving through the air or another fluid. The path of the spinning object is declared in a manner that's not present when the object is not spinning. You can see a small animation in this, how the trajectory of the ball is changing with respect to the time. Vishwa, can you play the animation? So look at this, how the trajectory of the ball is changing. This is the because of the spinning of the ball. So this is the called Magnus effect. We will try to understand like how the trajectory of the ball is changing in the next slide. So yeah, we will take the help of this image to understand the physics behind this, like how the ball is changing the trajectory. So in this image we can see that the direction of the flight of ball is from left to right and the air is moving in reverse direction from right to left. And the third one is ball is rotating in anti-clockwise direction. So in this we have to take two cases. One is the topmost point of the ball and one is bottom one. So in the top one we can see that the velocity component of the air and the rotational velocity of the ball are in the same direction. But in the bottom one we can see that these two velocity component are in reverse direction. So we can say that the velocity is more on the top one compared to the bottom one. So if the velocity is higher on the top one, so we can say that the flow energy is higher on the top compared to the down one. So if the flow energy is high, we can say that the capacity of the fluid is higher to overcome the pressure gradient compared to the lower one. So if fluid is able to overcome the pressure gradient, so it means that it is remains attached to the ball surface for a longer time, but in the down one it is less energy, so it will detach earlier compared to the top one. So in this image we can see that because of the spinning of the ball is pushing the air downward. From the Newton third law we can say that with the help of action reaction, if ball is pushing the air down, so air will also push the ball in the upward direction. And you can see in the image also there is a Magnus force acting on a ball. So this is the Magnus force which changes the trajectory of the ball. So yeah, this is the Magnus effect. So now we will move to the next. There are lot of interesting application of aerodynamic and hydrodynamic from sports to nature which is happening around us, but we are not aware of that. Like you can take the example of golf ball with dimples, banana kick in football, and the swing of a cricket ball, fighter jets planes fly in a V shape, and the last one is hydrodynamic levitation. And there are a lot of more applications related to this. So I will try to understand one of these, taking like we can take the first, like why golf ball has dimples. As we know that a golf ball having dimples on it fly farther, so it means drag force acted is less in this case compared to golf ball without dimples. You can see the trajectory of dimples ball and without dimples ball in a image. Like dimple ball has more lift and longer path compared to the smooth ball. So what is the reason behind reducing of drag force in case of dimple ball? So for understanding it, we will take the help of the next image. So yeah, in this image we can see two cases. One is the smooth ball and the other one is golf ball with dimples. So in the smooth ball we can see that air, the flow of air is separates quickly compared to the down one. In the down one, the attachment of the flow is for a longer time. So what is the reason behind this? The reason behind this is the because of the laminar flow and turbulent flow. In the upper case there is a laminar flow, but in the down one there is a turbulent flow. So why turbulent flow attaches for a longer time, and from why in the first case is laminar flow and in the second case it is turbulent flow. So first we know that laminar flow is a smooth flow and turbulent flow is a flow with fluctuation and having more energy. So it says that like in the second case turbulent flow is there, so it means it has more flow energy. So this is came because of the dimples. We can assume that like firstly it is laminar flow. Because of the dimples is like it's acted like a obstacle in the laminar flow. So because of dimples laminar flow transits to turbulent flow. So turbulent flow transition, it means turbulent flow has more energy, so it has tendency to overcome the pressure difference, so it will cling to the ball surface for a longer time. So if it's attached to the ball surface for a longer time, we can see that the vortex generated at the end of the this flow is very less compared to the first case. So this is the case like why golf ball uses with dimples, because drag force reduces with the help of dimples. So yeah, this is the reason why we use golf ball with dimples. So yeah, next slide. Yeah, second example is hydrodynamic levitations. Levitations means it's come from a Latin words levitates. It means that it is lightness. Is the process by which an object is aloft without mechanical support in a stable position. So let's look at a small clip of it. So yeah, this is hydrodynamic. It looks amazing, right? How this wall is in stable configurations. Yeah, I will try to understand these questions. Yeah, next slide. So yeah, here in this clip we have seen that water is getting thrown over and down by the ball. So the ball is pushing the water over and down, and from Newton's third law we can say that water will push the ball upward and inward, and so ball remains in stable configuration. The question comes to your mind is that like why water is clinging to the surface of the ball. So the reason behind this come into the picture is Coanda effect. So basically the Coanda effect is the tendency of a fluid jet to stay up attached to a convex surface. And the next one question comes to your mind is, next slide please, like how ball is stable in this configurations. Yeah, reason behind this is once the ball is levitating it is remain stable, because if it drifts too far into a stream that decreases the flow of water around the ball, hence reducing the force pushing it into the stream, and if it drifts too far out then water flow increases over the ball, hence increasing the force pushing it back into the stream. That's what makes the equilibrium position so stable. So yeah, next one. So there are like now you are thinking on that, okay, we understood, like you are just telling the application related. So there are some examples I will cover. The first one you can see the image of magnetic levitations. This is a maglev train where we use magnetic levitations. And the second one you can see is Magnus effect in rotor ship. Yeah, Vishwa, can you play the animation? In this ship we are using the Magnus ship. We are taking the advantage of Magnus effect, and these rotors are rotating because of magnet force, and these are act as a propulsion for the ship. So yeah, and the next one is, yeah, next slide please. So yeah, this is the most important one, like why fighter jet planes in weak formations. Have you ever this is the image of recent Rafale jets came from France to India. So have you ever thought like why these came in this weak formations, why they are not in other formation? So the reason behind this is aerodynamic effect. So the purpose behind this weak formation is to get a maximum ratio of L by D. L by D is lift to drag ratio, and have a better maneuverability, and also fuel consumption rate decreases in this case. So if all these advantages are we are taking, so it means that drag force is reducing in this case with the help of weak formation. But how it is reducing, we will see that in the next slide. So yeah, we will take the help of this image to understand the physics behind this. So we can see in this image is that a plane is flying. So after flying, it's creating a vortex because of its high speed. So you can see in the image vortex are generating into way. One is the downwards just behind the plane, and other one is upwards in the side of the plane. So we have two options: either we fly the other plane in the just behind the front one, and or we can fly the other plane inside of the this plane. So what are you thinking, which is one is better? So I think it's better like if we fly in the upwards of the vortex generated, because upwards is giving us a advantage because it's applying a force in upward direction, air is moving upward, so we are getting a advantage in free because of the vortex generated by the front planes. So yeah, we'll take the advantage of this upwards, and this is the reason like why planes fly in weak formation, like they are taking advantage of upwards, and because of this reason fuel consumption reduces to almost 20% of the fuel already we have taken. So yeah, next one please. So yeah, now you are thinking of, okay, we understood this phenomena and reason behind this, but what if we want to simulate this problem by ourselves? So yeah, for this, yeah, you can take the example of this image. It looks amazing, right? How this simulation can be possible. So yeah, for this you required a CFD simulations of these object. So for that you need a help of software Ansys friend. For this, Vishwa is expert in this field, and he will try to convince you like how you can simulate this problem in Ansys friend. So yeah, now I will over to the Vishwa. Thank you.
a third year mechanical engineering student at National Institute of Technology, Karnataka, and at the same time, I'm the. So I hope my audio is audible. I'm the JNCR Research Scholar from NITK for 2020, and so yeah, this is about me. So let's get started with CFD. So yeah, the aim for this webinar is why do we actually need CFD? That's the fundamental question that we'll try to answer through this webinar, and obviously like how CFD works and what are the steps which are involved, and we'll try to familiarize ourselves with the basics of CFD. Like, is it just like playing a video and everything starts working, or is it more about setting up the parameters it can go wrong, or like it's very complicated, or like is it something that an undergrad or someone who's interested can start learning? So all that we'll answer. So firstly, hopefully my pen is visible. So yeah, let's answer this question: why CFD? So what if there's no CFD? Just think of that question. So if there's no CFD, you need a lot of resources, a lot of money to come up with results, to come up with answers. Suppose you prototype something, okay? In days when there was no computation facility, you prototype something and you try to, get the answer, or like the lift force, the drag force, or the sort of flow that is there. Is it laminar or like turbulent? So you need a lot of setup, a lot of money. But with CFD, the only cost that is there, the only price that you need to pay is the computational price. So with that being said, it's very cheap. First of all, I don't know how well my handwriting is, but it's very cheap. It's almost like 10% of what will be required for an actual setup to be there, a vent tunnel facility and everything. So it's just the computational cost that you pay. And then yeah, let's get started with the steps which are involved. Before that, like a formal definition of CFD. What is CFD? It's actually a numerical experiment. It's a numerical experiment done to analyze a particular flow problem, using the conservation laws. What are the conservation laws? Mass conservation, momentum conservation, and all those equations. So this is a very cool. Let me use laser point. So it looks pretty cool, yeah. This is what gets a lot of people interested. So we'll look into that. So how do you start off? So basically, you need something that you will be testing, yeah. So you need a CAD model first off. So for both type of flow problems, where like there's this external flow and there's this internal flow through pipes and veins and arteries, and a lot of questions were there, like how CFD is used. So basically, it's for biomedical purposes. It's there, and for a lot of other purposes. CFD is like a test for failure. What can happen? So have a CAD model first thing, and then what happens? Then you prepare a domain. So what is domain? So when your computational, like it's going on, you can't compute the entire world. You need to confine your focus in a set, or like in a set of points where you'll be looking at the flow and the variation of pressure, all the dependent variables which are involved. So that's called the preparation of domain. First, CAD model, go for the preparation of domain. Secondly, we go for mesh generation. Now, mesh, like new word. So what is mesh? Basically, it comes from the idea that in computation, you can't go for continuous things. You can't go for infinitesimal. Like in calculus, we talk about infinitesimal small variables. So like even a trapezoid, like a trapezium is like a rectangle there, or all those things. So no assumptions over here. Those sort of continuous assumptions fail. We go for discretized systems. We assigned every section of our domain as as a value. Like this much section, the value of that section will be at the center, or something like that. So you divide the whole domain into subparts, grids, call it subdomains, control volumes, small control volumes. Where the conservation control volume, and that is called the mesh generation, and where you discretize the domain. So it can be, you have two choices basically. So your domain is full of water. Okay, your domain is like free for. You can see here the domain is free. These regions are free to fluid to flow over, and this is not there. This is cut out from there. Okay, so if this is cut out from there, and the fluid can flow over this. So it will not flow. It's an obstacle. It's a wall for the fluid. So it will show certain characters, certain behaviors, like how it will flow. So we'll analyze. And the second one is like, you keep this part and the rest empty. So that doesn't fit into the computational idea, like emptiness means what? So yeah, we go for basically the first approach where we cut out the CAD model from the domain. So yeah, next is refinement, the refinement of these grids which is there. So how do you refine these and why do you refine these first of all? So basically, I'll get onto the mathematics of, the grid size and everything. But just know this, the smaller the grid size, the better you'll be able to capture the gradients, like different dependent variables are there, temperature gradients for heat transfer and other things, and pressure gradient for CFD, pressure gradient, or like, the gradient of a velocity for that matter, you'll be able to catch those variations more better, like near the wall you can see over here, yeah, or like these regions where you need to capture those gradients, those small deflections, you need to refine your mesh and get good results. And there's like this inflation that we'll talk about and other things when I go for the live demo. So again, the mesh thing continues. What is basically happening? So basically, this is a mesh ka small part, like a small control volume or like the subdomain or the cell. So you basically try to find the physics value or like the value of certain dependent variable at the center, and you extrapolate or like interpolate it, for the entire surfaces or the volume. So basically, you just know one value for a cell, and then you try to, somehow, predict the other values using interpolations. So here you see is like it's a mass flow, conservation, and this is like momentum flow conservation. So you just consider this small volume and you try to apply these on these infinitesimal volumes. And actually, these are not infinitesimal for CFD. They are like finite. So you have different methods. So basically, in CFD process, you need to be very well aware of these variables, pressure and velocity. You can't afford to not know them. So, and then the basic conservation law. First is mass and momentum. Second is momentum. So, what is this equation? A lot of people get scared and they just run away from those beautiful flow simulations just because they don't understand the PDEs. So, this is partial differential equation. And what does it say? Is it says nothing for a layman. But if you want to put it in a layman's term, it says that the in mass flux is equal to outgoing mass flux. And in mass flux minus outgoing mass flux will give you the rate of change of mass. It's very simple. Like it's everyone who wants to understand will understand that this is a control volume. Mass is coming in, mass is going out. So whatever accumulation of mass is there, it's because of this influx. So that is what this means. And how does this represent that? So basically, it's like change of mass, dm by dt. And here in this equation, we divide everything by volume. So m by v. One sec. So this equation over here, it's actually dou mass. Please bear with me. So dou mass by dou t plus the flux, like the flux. And you represent the flux by a divergence, okay? So anything that is coming in or coming out. So the divergence of something like somewhere where the mass is coming in will be negative, and for something which is going out of the given volume, it will be positive. So you use this operator of divergence on rho and velocity. Why rho? Because as I told you, this mass is not mass, this is actually rho, as the whole equation is written in terms of mass of that small volume, small control volume, but it's divided by volume. So the whole equations that you get here are in terms of rho. So this is so simple, yeah. And this constitutes the mass conservation, or something that people call continuity equation, which is different, right? We'll talk about it. So momentum conservation again. So another new term is this capital D. So this is called the total derivative, which takes care of the fact that the variable which is which it is operating on is it's studied both with space and time. So you change in U with space and time is studied with the help of this. Oh my god, yeah, laser. Fine. So with the help of this and the other terms, let me just answer that as well. So this is, other terms are the stresses, the shear stresses acting on this, this cube that you see, like this or this, all those effects, force balancing and momentum balancing, and then the source term is here and the pressure term. So this is like a bit of the explanation. So basically what happens? So a computer can't solve like a differential equation like a human, obviously, because it doesn't have brain. Neither it can go for those, manipulation of terms to integrate something. So it needs a method to work upon, and how does it get to that method? That's important. How does it get to that method? So there are scientists, and a lot of people might might have studied that there are numerical methods which boil down all the calculation to a formula which is like iterations and everything. We'll get into that later, but we want to give the computer an algorithm. Be like, okay, this is what you're gonna do. Just keep doing. You have no brains. You can work and just work for it for us. So basically it can't do that. So we divide the whole domain into like discrete volumes or discrete grids. Where we solve for these conservation laws and get the value of different variables. And then we use these techniques such as numerical methods such as Simpson's 1/3 or 3/8 to get the like the value over the to integrate the value and to get the result. So basically, when you apply these methods, what you get is like a linear equation, like set of linear equation which can be solved using a lot of iterative methods are there, Gauss-Seidel and SOR. So ultimately, what you get out of it is like a lot of data. The more detailed the simulation is, the more chunk of data you get. So for people who are interested to know how the flow is, you're gonna go crazy if you look at this thing data. So we solution is not for the thing for us. We go for post processing where we visualize stuff. So basically, this is what happens. A PD is converted into a linear system of equations, and then you see here, like I was talking, this flat domain, 2D domain over here, it's divided into these small points at the center, mostly at the centroids. That's the convention. So the values are calculated at this, and then we interpolate it over the entire this thing, and then you see those beautiful simulations of probably like a cavity simulation and everything. So and few terms. Let's just before we head into the live demo, this is just an overview, and I'll show you during the live demo where these particular terms are used in Ansys, and Ansys is the software basically we're gonna go with. Okay, so turbulence. I don't know whether the spelling is right, but hopefully it's right. So turbulence and chaotic. Okay, what is turbulence? So basically, it's the chaotic change in the fields. Fields can be anything: pressure field, velocity field. If you're doing MHD, magnetic field, it's an unpredictable change in the fields with space and time, which no one can predict. So that's how it is. Then viscosity, it's analogous to friction in like solids. So it's basically friction between two moving layers of fluid. So basically, suppose this layer is going and this layer is also going with it. So there are some molecules which are transferred. They transfer some momentum and they slow this down. Something that you might have seen in rocket propulsion and all that. So that is what happens. Okay, so friction. This is like a friction effect between the layers. Reynolds number. It's basically a measure of like which force is dominant, whether the inertial force is dominant or the viscous. So if the inertial force is dominant, what is inertial force? The movement force. The acceleration force. All those forces. If those are dominant over viscous forces, then we say it's a large Reynolds number flow. Like high speed flow and all that. Okay, so now summing up, now what do we know like as a high school as a high school kid or like a 12th grader is that we know continuity in fluids, we know Bernoulli's equation. Now what has happened now? So basically continuity is based on the fact that we have the thing that we learned, A1 V1 equal to A2 V2. It's based on the fact that the fluid is incompressible. Even the Bernoulli's equation is based on the same fact. and a lot of assumptions, are taken that it is non-viscous, inviscid flow, and all that. So if you have time, you can just neglect certain terms which I'm saying. Keep the just neglect the dou rho by 2t term, because that accounts for compressibility. Rho is changing means you're compressing the liquid. Just neglect that term, neglect the viscous term. So you can land upon Bernoulli's equation. So basically, this is a bigger set and this is a subset of it. So this is how it works. Incoming mass and outgoing mass. The difference of this will give you the increase in the mass in time dt. That's what I explained. So you see there are so many equations. So this is for suppose you have a general flow, compressible flow, unsteady flow. So you will get this sort of general equation for mass conservation. And for steady, you will get this. Density won't change with time. The change of density with time will not be there, so you just get this thing. And for incompressible flows, like when you're talking incompressible, so obviously rho is of no use. You can just put it out of divergence and take it other side, 0. Second equation, the two main equations that we're talking about here, Navier-stokes equation, is like the mass and the momentum. So you need to do a bit of momentum balancing and force balancing on that small control volume. And then what follows is, you ending up to get this equation. Now again, don't be scared by these terms. You just look into the definition of it and you'll be able to get it. I'll still explain. So this is like mass into acceleration is equal to sum of all forces acting. Take it that way, it will be very easy for you. Okay, so now as I told you, whatever you learned in your 12th grade was like an ideal stuff, but there are turbulence as well. And how do you model that turbulence? Because turbulence is something that no one has understood. It's very erratic. You never know what might happen. But we need to study things and we try to get the best approximation for a particular problem. You can never say that a particular turbulence modeling this thing will give you the right solution. Okay. So there are 3 methods that are there: DNS, LES, and Reynolds average Navier-stokes equation model. So let's quickly go through it. The theory might be taking some time, but don't worry, it will be worth it. Because I can just go through the simulation and show you, like, guys, yeah, it's working. But it's important that one understands, because people show simulations, people talk about simulation, but what's happening behind, no one talks about. And that's what the aim of this webinar is. So, what is DNS? DNS means direct numerical simulation. You solve everything. Basically, solve the equation properly. No models, nothing, 0 models. Equations are given. Just keep on iterating. Take 2-3 days. Solve the correct equation. You get beautiful vortices and everything, and eddies and everything. It's just amazing. Okay. So this is DNS. Takes a lot of time, but we don't want that much of details. We're just interested in lift and drag. So that's why the mean flow or a bit of approximation will work. So we go for LES, which just solves the large eddies. You can see here, just the large eddies, and neglects the smaller one. So it's like suitable enough. It's very accurate. It's very accurate. That's what I'll say. And then comes Reynolds average Navier-stokes, which is like very commonly used. Like Ansys also uses this Reynolds average Navier-stokes. There are options to change sort of methods you'll be using. But yeah, this is generally used and just gives you a brief idea of how the flow is around a cylinder. Okay, so it just solves for the mean velocity. Next is K epsilon model. It's a very famous model. That's why I decided to put it over here. So basically, what happens in Reynolds average Navier-stokes, we can have further discussion, but since it's like a short webinar, so I'll just talk a bit about it. So you get terms like these, like the mean of the fluctuations, so you can take turbulence flow as like velocity, mean velocity, and the fluctuations over it. Okay, so these fluctuations need to be accounted for, and you need equations to tell what these fluctuations are. So there are these models which are proposed by certain scientists, and the hypothesis given upon their names. So you can model the turbulent viscosity. Again, this is the property of the flow, not the fluid turbulent viscosity. And other thing like kinetic energy of the turbulent fluctuations. So you can just find the kinetic, and these are just assumptions, hypotheses. No one has ever proved this, but these works for a certain type of problems. That's why we use it. Alright, so near wall modeling is another important concept. So, near the walls, these models fail because the viscosity is too much, like the fluid is flowing and the friction below the wall, it's imposing on the fluid and it's pulling the fluid. A lot of viscous effect is there, so we can't go for the same model LES or like turbulent models like K epsilon. So we need to model it separately. So suppose this chunk is solved and near the wall we solve something else. So there are two approaches: wall function and low Reynolds number modeling. Wall function is basically you assume a function like a log function for certain layer. Inner layer is divided into viscous sublayer and all those things. So you assume certain functions over there, and then here you just try to make the grid smaller and just try to study the using low Reynolds number models and solve it. Cool. So discretization, important part. So how is discretization come into picture? So basically what happens is let's look at this first model, which is finite difference factor. So basically we use Taylor series, which is a wonderful theorem or series which helps us to write a function in terms of its derivatives. So yeah, so you see, like suppose you want to find a term like this. So this is how in terms of differences, this is not differential, this is differences. So in terms of differences, you can write it this way, and you can have some residual terms. So that's another, it gives you another insight into CFD, that it's not the exact solution, it's just an approximation. How close can you get? You try to reduce these terms, like the order of the truncation terms, these truncated terms. If you reduce the order of those terms, this thing increases. The accuracy increases. So I told you about refining the mesh. Now I'll try to bring it into the picture. So suppose if del x is very small, it means that this term will be small. So the accuracy of the solution will increase. Yeah. So that's why we need finer meshes. So just concentrating at this particular point. So finite difference, you just split it into grids. Okay. So don't worry. So you get this point and you need neighboring points. So we just do everything in the interior. We don't go for the wall points because we need to specify boundary conditions. Another important thing, boundary condition, why are they required? Because the boundary flow is different from whatever is happening inside. Okay, so you look at this thing, xi and this is yj, but like yeah, you can look at this particular point. So using Taylor series, we can model this. And what is finite volume used by Ansys? So basically, large volume, broken down into chunks, and you have a centroid. And using a Gauss law, like Gauss theorem, I think, yeah, Gauss theorem, you can convert these volume integrals that you get over here, different convection terms, diffusion terms, source terms. You can convert them into something which is, like integral over area, and try to reduce the computation idea and everything. So what happens is basically the dependent fields in this limited volume are actually solved on the surface. So basically suppose this is a velocity field, you just solve it on the surface. You just solve it on the surface and you get it for the entire volume. That's the beauty of Gauss theorem. So again, like numerical methods for modeling. So basically Navier-stokes discretization I was about to take, but I decided not to take because this will take a lot of time and we won't be able to complete the live demo. So I'll just go for the 1D steady state with FDM, 1D steady state heat transfer with FDM, and a simple algorithm which is used by Ansys. Okay. So this is the first heat transfer problem. So basically, how do you what's the question over here? The question is there is certain temperature given over here, certain temperature given here, over here, and here, and here, and then you try to see how the heat temperature develops over this. So so the equation that we use is like second order a partial derivative term. So a very famous and so yeah. Plus you have a source term which is basically the heat generation, and dou square t by dou y square plus dou t square dou square t by dou x square plus s is equal to 0. Okay, this is very confusing. I mean, okay. So this is how complicated it looks, and look how CFD just cuts down the complexities. And if you go for the analytical solution, you'll know how painful it is to solve this. So yeah, Taylor series again. So Taylor series for this particular point over here, you can write it like this. So what is Taylor series? F of x plus h is equal to fx plus f dash of x into h plus h square by 2 into f double dash of x, and the life goes on. So this is what it is. Okay, so small change in this coordinate, that is m plus 1, written in terms of the previous coordinate, and the small the series that continues. So we'll truncate it and try to approximate. So these are the 2 points we interpolate, wrote Taylor series for, and then we plug in over there. So that equation that I wrote becomes something like this. It's a discrete equation now. It's a discrete equation, and then if you think that there's no heat generation, this term goes away, and you're left with this thing. And assuming that the grid size is the same in x and y direction, you get a linear equation. So now think of linear equation and think of this differential equation that I wrote over here. Beauty of computational fluid dynamics, that's what I'll say. And then yeah, you get a set of algebraic equations, and you are smart enough to use Gauss-Seidel and other iterative methods. Give it to your computer, it will solve it, and you will get a bunch of data. Use some software like MATLAB or like inbuilt softwares like Ansys. They'll give you a representation. So another one is like simple algorithm. Basically, it's used by Ansys, and simple algorithm. Okay. So basically, it's basically for pressure. So when you solve Navier-stokes equations, what happens is like the pressure is nowhere to be found. You can't explicitly find pressure anywhere. So it was developed to tackle that thing. You can read it over here. Discretized momentum equation and pressure correction equation is solved implicitly. Where the velocity correction is solved explicitly, and this is the reason why it's called semi-explicit. So one is solved implicit, one is solved explicit. So here I'll just highlight it, and we are just done with this, and we'll go for live simulation. So this term in the set of equations, you see this is the trouble. Velocity is here, velocity is here. Okay, so for all the variables you can find it, but this pressure is nowhere to be found. So simple algorithm helps us. So first you guess what is the pressure, T star, and then you try solving for the first few values of u that you get, u, v, w, and then you find what is the P dash. It's the difference, or like it's the error in P. Okay, and once you find that error in P, you again go to these equations again, and you find new uv, and then at the same time you correct the pressure. Guessed pressure plus the error will give you the new value, corrected pressure, and then you go on looping till the time you end up on a converged solution. And these are certain methods that we can use. So basically this is the summary. Pre-processing, which involves boundary layer setting, material setting and everything, and involves the meshing and everything, which is like creating discretized cells, and then simulation, and then post-processing. So now is the time. I hope most of you would have stuck for this, but yeah, now it's time for live simulation. Just give me a sec, I'll set up things. Okay, alright, just wait guys. Okay, alright, so hopefully you guys can see my screen. Yeah. Okay, Nitish, you can tell me if my screen is visible.
The window is visible.
Yeah, is the screen visible as well? Like the Ansys workbench?
Yeah, the cylinder 20. Yeah, it's visible.
Oh, all right, cool. So, guys, this is how Ansys workbench looks like. So the way I talked about it, CFD involves the CAD model, which is given in the geometry. It involves meshing, which is discretizing. It involves setting it up, boundary conditions, and solvers, and models, and everything. It goes in setup, and then the solution part. It solves it, and then you get post-processing through results. So just to save computational time, I have just solved it beforehand, and so that we don't take a lot of time, but still, let's go through it. It's better. So you right click. So how do you get this? First of all, I would like everyone like who's watching, even if there's like single person watching, just type your doubts as I go through the simulation, and I'll try to answer them. As I get time, because this is going to take some time. So if you want a time limit, like in 10, 15, 20 minutes, we'll be done with the simulation, and I'll be explaining, and then we'll go for like Q&A. That's the maximum that we'll take. So firstly, you are dealing with Ansys Fluent. So how do you get it? You get it from here. This is the whole package over here. So you click on it, you get this thing. Let me click. So you get something like this. I got it. So you'll get a lot of question marks over here. Okay, and those question marks will be ticked when you do that part. Okay, so that's very good. So let me just delete this. Okay, so let's get into geometry. So you can import your geometry from here. You can make it on any of the CAD softwares and import it as like a .stp file, or like a lot of time STP works in IGES file as well. And then you just import it, open your design modeler. So what is design modeler? It's just a module where you import the geometry and do some geometrical changes, whichever are there. So it's opening. Nitish, just let me know if you can see this design modeler part.
Yeah, it's visible. Yeah.
All right, cool. So guys, what you see over here is like a domain, a 2D domain. 3D will take a lot of time, and we want to make this webinar short. Yeah, 2D domain with this circle cutout. So this circle is the cross section of a cylinder. As I told you, you just need to cut out your CAD model. So our CAD model was basically a cylinder, and it's cut out of the domain. So how do you make it? You just import it first thing, and then you need to take care of the fact that this is one single body that you're going to simulate. If it's a flow simulation in a domain, external flow especially. So how do you do it? There's this option of Boolean over here. So suppose you've got two parts, a rectangle and a square. So you use Boolean, and you subtract this cylinder from the rectangle, and you get this sort of model, and you get one part over here. Okay, you need to check its properties. It should be fluid. Once that's done, just hit generate. Life is set. Escape, and then you'll see a tick mark over here, and you can just update this, and then you go for the meshing. So you open the mesh. Guys, I'm open for questions. Like if anyone has any questions, any doubts till now, they can just put it in the live chat box, and I'll be very happy to answer. Okay. Unigraphics file, I need to check. I'm not sure about it. I think you can search the internet and you'll be able to know. But I think if you want to open any CAD file, you need to import it, in a .IGS form or like STP form. So just take care of that, and probably you'll be able to open it. So next is what is next? Yeah, so we have opened meshing, so we need to mesh this. So basically what you can do is just come here, and click on generate, and it will generate the mesh. So I'll show how I did the mesh. This is my mesh. So I was talking about a lot of things like mesh refining and other things. Yeah, they are very important. So if you look at my mesh, you'll see that near this part, it's really dense. It's really dense, and it's kind of growing in a circle. So that is the part that is called like inflation, or like inflating a layer. So you just so how it's done. So firstly, I set the type of mesh that I want. So I was looking for triangular meshes. Wasn't really important. Then I went for like edge sizing. So how do you get this? You just come to mesh, you right click, you get all the options over here. So I went for edge sizing, and I sized this like 50, I remember. So you come here, and you can put the size over here. So once that's done, you can go for inflation and face sizing and other things. So what is inflation? You just grow the layer over a certain size. So I'll show you guys that thing, mesh again. So yeah, you see at the center there's like the center over here, there's a lot of dense this thing. So we can get good values, like really catch those fine fluctuations and everything. And then there is this face sizing. You can set the size of the face. So everything you can get from here, and the name is like self-explanatory. That's the beautiful part about Ansys. And another important thing that you need to do in mesh is like name selection. So what is name selection? So Ansys uses these names to know what is like your inlet, your outlet, your domain, and everything. So I've given like a wall. So wall, you can see this is wall, and inlet, this is inlet. So the fluid will come in like this. This is the outlet, and then there is the cylinder. So this is how you set up. So suppose I want to name select cylinder. So how do I do it? So basically I select it, left click on it, and then right click, and then go to this create name selection. Or you can just select it and press N on your keyboard. You can get that. So with that being said, suppose I want to give it a name like cylinder 1. Okay. Hit OK. You get this over here. Yeah. So that's you can just put the name selections over here, and I'll just delete it because I already have one cylinder. So with that done, you can just you're done. That's all. That's all that is required for meshing, and then you get back to your this thing, update it. You can even close those modules which you're done with. So yeah, it'll take some time. It's done. Next step, setup. The setup is where people have a lot of issues, like what is how many solvers and everything we need to use. So I already did it. So what you see right now is like a report of CL and everything fluctuating. Okay, I should be switching like this. So basically, so one sec, I need to close and open this. Close it. Okay. Basically, it's like very demanding computationally. That's why. So this will take some time. Alright, so if there are any questions, you guys can ask, because this is gonna take some time. It's not responding now. Anyways, so basically you go to the setup and you do certain things, and like setting up the model, setting up other things, and then you come to solutions. So one sec. Let me close. Alright, okay. So it's not responding. Alright, so there has been some issue regarding this. But yeah, basically there's the setup part. It's not responding right now. So It's gonna be hard. So like, let's just wait for a while. Close this program. So I mean, this is another thing that you have to be patient with, is the fact that these softwares are like really heavy softwares, and they're gonna take some time, you know, to respond or yeah. Okay. So basically, I did it beforehand. So now it's asking me, should I? So okay, so it's opening. So yeah, we're looking for double precision. We want the mesh to be displayed, and I'm using you know, like solver processors 4, and you know, number of GPUs per machine is 1, and then I start. So we are starting off the setup, and this is the last and the important part of you know, Ansys Fluent, where you define all the conditions, where you define everything. And you know, that's why I took some time to explain the maths behind it, because here it's everything is GUI and you don't see Navier-stokes equations anywhere, you know. So yeah, okay, some more time, and just need to wait. So just be patient with these softwares, and cool. Fine, so here we are in the setup of this. So you see this very dense thing. This is our mesh. You know, you can see it more pronounced that I've made it very dense over here, because the flow near the wall is very important for me, for anyone who's analyzing the flow around anything. So you just select the size of that edge, then go to the option of inflation, and then, you know, inflate it. I made it like 40 layers with a growth of 2.5. You know, what is 40 layers? 40 layers one on the top of the other, and yeah, and then with a growth rate of that. So yeah, let's look at this. So I'm gonna simulate. You should know about your problem. Okay? So my problem is like a von Karman effect problem, where, you know, there'll be fluctuations in flow and everything. So I'm going for a transient, you know, flow simulation, which is pressure based. If you go for density based, it is actually it's going to be like something like compressibility thing, you know. But we are not going for like compressible flow, and absolute velocity formation and planar. So this is the general setup, and then you go for models. So like what I was talking about earlier. So there are different models which are there. Let me just show you that. So yeah, you see a lot of models over here, and you know, for viscous model, you see, you know, there are certain models given. So here, K epsilon, the one I talked about, yeah, it's there. The K omega model, and a lot of other models are there. For this one, we use transient SST, you know, which has 4 equations. So 4 equations shows, you know, like in the model, like I showed you for the fluctuating flows, you have like, you know, related it to the turbulent viscosity and other things. So there were like 2 equations there for K epsilon, and for this we have 4. So we'll just select that, we'll hit OK. It's very simple from here on. And because it's GUI and you don't need to code, so that's done. Let's go for the material. So the fluid, I will go for air. Where you can see the properties here. You can change it if you want, and click on change and create. I don't want to create anything, but for demonstration's sake, let me make it air 1, create and change. Do you want to overwrite? I'll say no. Anyways, let me just close this. So I'll be going with air. Air as my model. Cool. Air as my model, and create and change, and that's fine. Okay. So you can see air 1 as well, but if you want to use it, it's basically the replica of this. So you've selected the material. Next is boundary layer. Just forget about this cell conditions, it's set automatically. So you see these things over here. Pretty important things, yeah. Because this tells you about the name selections that you did. Okay. So name selections that you did, the interior of the body, the inlet, the outlet, the walls, the top and bottom walls that you selected, the cylinder. So how do you set the boundary conditions? So for inlet, let's try to edit the inlet. So editing it. Yeah. So for inlet, you see I'll set a velocity of 200. So 200 meters per second the fluid is coming. I don't know what the Reynolds number is, so I don't know how the flow might come up. But you can do the calculations and you can be sure about it. So everything you need in touch, it's about the turbulence and everything. So just you can change the values, turbulence viscosity ratio as I showed you in that model. So you can, depending on what you think might be the right condition to suit your problem. So again, I said models are just hypotheses for different problems. Okay, and then outlet, basically we go for zero pressure. You see here, zero pressure, gauge pressure zero. So anything above it will be positive, anything below it will be negative. So done with this. Done. Just neglect these because they are talking about mesh interfaces. If you have two things in the domain and you want to talk about like how the interfaces are coming together, you need to bother about it. And once you hit on check, there's this option of checking here. You'll get to know what all things you need to manipulate. Okay, so we're going for basic simulation over here and trying to soak in the software. So you need to look into these. You can put like reference frame is obviously somewhere here. You can see somewhere here, and other functions, named functions. You can define your functions over here, which you want to see, like lift, drag, which is obviously there. But if you want some other things. And then, so these are a lot of reports that I put in, for like different reports, basically CL, CD, and everything, which I want to find. You can just right click and edit and add yours, or like go for new. You'll find a lot like force, drag, lift, moment. Beautiful software, isn't it? Needn't compute anything. So yeah, with that done, don't worry about anything. Monitors you can set. But just go and hit hybrid initialize. So you will set the initial conditions for your simulation and then Shirmadi again. I mean, what I said means like just relax and then yeah, you just need to go for here. So here again, the calculation and solving part is something tricky and people don't understand. So you go to this auto save option over here, and you make it one, like save data file every one time step. So if you want that moving simulation of flow, you need to like have data registered. So this will make assure that, and then just chuck everything. You can look at solution animations, based on different graphs that you get. Would we leave this for now? And any questions, guys, just put in, and I'll try to answer it once the solving starts. So yeah, okay. Now this thing. How you wanna compute your simulation. So basically I'm looking for 50 time steps and 5 iterations maximum I'll give for each time step, and the time step size is 0.01 seconds, and the reporting interval is 1, and this is also 1. Everything is suggestive, and let's just hit calculate. Everything seems fine. So yeah, and these messages will start popping up as you start solving, and you'll see the progress over here. So whatever residuals were there. So what are residuals? You assume something, and you have like the difference, the successive answers is the residual. Like whatever you predicted, and like the next prediction. So the residual should try to go down and converge at a particular point. That's what we look for. And right now what you see is like CL versus flow time. It's weird because it's a transient flow, one common effect. So just bear with this, and what you'll see in this simulation is the fact that things that you get from simulation aren't always right. They might be very vague, wrong, and you need to, that's where CFD requires brains. It's not a software that can do everything. You need to understand the value solution by like humans. They can think and they can try to analyze it. And so in the meanwhile, I would like people to ask questions. So someone saying, Rohit is saying that how do you know if the mesh is correct? Okay. So mesh, basically what mesh is, ideally what everyone wants in mesh is like, you can find the flux flowing through the boundaries of that mesh. So every time the mesh is like too skewed or weird angles and, weird mesh, you can always hit on this this thing or like check case over here. These two buttons, they tell you the improvements you need to do. Okay, so you go and check the quality as well. That's in the software. But like talking in theory about like the mesh and everything, it's basically it's a whole domain of study. But basically, you need to check the skewness and check the fact that the mesh is not small. There's this number. I don't know, current number or something like that. Current number. I'm just completely missing that number, but that number should be less than 1 if you want like good simulation. Basically, if this is your domain and the fluid flows through the domain before even like one time step has happened, you'd miss a lot of stuff. Mesh sizing and everything need to be taken care of. And as you can see, we are getting very weird PL curves over here. So, any further questions, guys? Okay, so I hope I answered your question, Rohit. And okay. Yashaswini, could you explain the options in method under solutions in more detail? Okay. So once the simulation is done, I'll try to answer that. So solution. Where is solution? So okay, cool. I'll try to get to that. Methods, fine. Any further questions, guys? So basically, methods are solving methods are different. You can go for like DNS, LES, and branch methods. Basically, trying to cut short on the computational time. Like suppose if you're looking for a jet which is flying, you don't want to look into the eddies, very small eddies. You just want to see the CLCD. Yeah. So you'll probably go for a RANS model. So yeah, we're done with the simulation. And you see like a very characteristic, eddy simulation. No, like transient simulation over here, fluctuating but yeah, you can see that we've got some amount of like ratio of residual, so it's like 0.00 times something. So yeah, this is done. This is done with this solution as well as setup. And we'll go for results from here on. So someone is talking about the methods. Let me just look at it. So Yashaswini, I'll try to explain this part over here. So as I told you, the scheme simple, which I showed in the this webinar before. So simple stands for semi-implicit pressure linked equations. So we don't have, you can just go through the slides and, basically trying to get some value of pressure somehow. So, you can look at this gradient, which is least square cell based. So, again, it's something which is, from the very basics of the CFD where, I need to start getting into finite volume methods. And it will, it's basically how you define the, the discretization, it's based on that. So, if there's this volume and you want to check the gradient of something, so you go for like least square cell based discretization. And so second order, basically whenever you're solving any equation and you go for second order, definitely the truncation, the term that you're truncating out affects your answer and everything like that. So just we go for higher orders. And upwind, this thing, it's again like into the CFD where you try to justify the flows from one cell to the other cell, orthogonality and everything like that comes into the picture. So if you want, I could share the resources with you. You can join the live session and I'll share the resources with you. You can go through that. And transient formulation, again, whenever we're talking about the order, what we're trying to do is trying to truncate it one step further, where the order O of delta x, it's in square, so that the effect of residual can be pushed down. So basically that's it with things. So we're done with setup and solution. You can see 2 ticks over here. We'll go for results now. So there we go. So this is the final part, which is the post processing, and after this, like the whole simulation is done. Like the whole idea of having a simulation, and so you'll get the visualization and everything. So yeah, what you see right now is CFD post, which is courtesy of Ansys Fluent. So yeah, this is the sort of profile that you get. Just need to be a bit aware how you handle this. So yeah, you can manipulate it from here. So you get this. Let me just uncheck this. So you get something like this. You're like, oh my god, where's my flow simulation? So what you do is you go for some contours, and I want to check for velocity. Let me write as velo, and okay, and then you get like some options over here. So yeah, all domain, you want to go for all domains, and then I talked about symmetry plane when you were talking about domain. So it's a plane that divides from the middle. So you've got 2 symmetry planes, one on this side and other on this other side. Select one symmetry plane, select the variable that you want to see vary. You can go for a lot of things. So let's go for velocity first, and this is like a RANS model. So you won't see those eddies, that with that much of clarity. So let me have like 100 contours and apply. So there you see, like just a rough flow. You don't see the like the flow curling or something like that. And if you want to visualize it, you can hit this option over here and go for time step animation. Hit play button. Just wait. So you see how the flow is developing. You can see over here. You can see on the walls. So this blue part is like 0 velocity, and all the other parts in the middle is different velocity. So you can see the domain is having certain velocity. Yeah, 200, and then this is like at 0, and so you see like some velocities being developed over here. Yeah, you can see certain velocities being developed over here, and you can see some flow separation happening. This blue part, stationary fluid just leaving, and this is tiny bit of fluctuation is there, and you see point of stagnation over here, and you see that fluid is speeded up over here. So yeah, I mean this is the whole idea of CFD. If I can look at the flow, if I can look at the colors, I can understand how the air is flowing, and I can design my thing that way. Designing, studying certain phenomena. So this is what like concludes the whole idea of CFD. And if any questions are there, I would be very happy to answer them. And anything like regarding MATLAB, also a lot of people were asking questions. So I think you can simulate things on MATLAB as well. Flow simulation. There are some add-ons, tools that you can use. But definitely, no one will recommend that for very complicated flow problems. Go for some commercial software. And if you're not, if you want to understand the basics, go for some open source software, for CFD, which I'm currently working with. So that gives you a lot of freedom to code your own problem and be more involved. So that's it with the live demo, and the other features which you can explore once you do it. So with this, I would.
Sure. There is one question missing by Yashaswini in the live chat section. Here in Reynolds number, L is the length.
Okay, one second. Go on.
I think here in Reynolds number formula, L is length, right? So if we consider the length of the domain or the diameter of the cylinder.
So, okay, I can't see the question. Where's the question, by the way?
Just about the, can I explain the options in methods if you know that question before?
Okay, yeah. Okay, yeah. So, yeah, question, Yashaswini, the fact that, Reynolds number is just a dimensionless number, trying to understand the flow characteristics and everything. So, it's basically the characteristic length of anything through which, like, the flow is happening. So, in cylinder's case, it's the diameter of the cylinder that will be facing the flow. So, that's the length that you consider for Reynolds number. It's not the domain, it's the CAD model that you're using and the characteristic length of that CAD model that you will consider as, for your Reynolds number calculation. So it's the characteristic length. So here it's the diameter, which the flow is facing. So I hope I answered that question. And there's another question from Suresh. Can you please tell me whether the user define function file? Okay, UDF file. Okay. I think I'm not well versed with UDF files as far as my knowledge is concerned, but I'll definitely try to get back to you on that. Yeah. So, any further questions, guys? Okay, we had a lot of questions during registrations as well, so I would like to answer them. Just a sec. So,
okay, I think okay.
Yeah, is that fine?
Yeah.
All right. So, just a few questions. So, very trivial questions which I would like to answer is, so, how to get started with CFD? This is one of the questions that people ask. So, to get started, watch some videos, start doing the simulation, and start understanding the physics once you get the results. So that's how I started. You can follow a certain book. You can be under someone's guidance. If that's not there, don't worry. Just start simulating things. Start learning. That's how you can start off. Yeah. And slowly understand the maths. So for me, it wasn't like maths first, it was these beautiful simulations which I started. And CFD is a new topic, so, okay, start from the beginning. I hope I started from the beginning. More about the research, CFD is humongous, from biomedical application to fluid structure interactions to what Sagar talked about, like turbulence modeling and, like the golf ball dimple and all those analysis are there, sports modeling, and, these sort of things are there. And a civil engineering application of CFD, obviously fluid structure interactions. So suppose you're building a bridge and the wind starts blowing. So what will happen? The bridge will also start flowing, and the whole structure will start vibrating. So that kind of issue can be there. So that's sort of what happens with like in civil for CFD. That's what I know. And you can obviously go for some environmental engineering, and you can simulate the atmospheric boundary layer and other things are also there. So, okay, MATLAB and Simulink, as I said, they are not the software for CFD. If you really want to get into hardcore CFD, you need to go for some open source or like in the software which are available like Ansys. MATLAB you can simulate, but you need to write lengthy codes, and I am really not sure like how much that will be of use, because most of the good simulations are done in open source softwares and these things. Heat transfer studies, obviously, like the one I demonstrated using FDM, you can do heat transfer studies. That's the part of CFD. And yeah, I hope I answered the advancements in math behind CFD analysis. if Sandeep Reddy is like watching this, I hope I answered. Industry-oriented projects, like I said, a lot of projects can be done, like IC engine kind of problems, and then the like heat exchanger kind of problems are there. And obviously, if you get into automobile, you need to go for aerodynamics and thermal modeling of certain things are there. And okay, solving CFD equations, like how to find solutions to those partial. Okay, so partial differential equations, obviously there are certain methods for analytical solution, but hopefully I explained how you can deal with them using Taylor series like FDM. Finite volume method is also there, where you discretize things and you get the results. So okay, so that sums it up. Over to Nitish. Thank you.
Okay. Yeah, thank you, Vishwa and Sagar. Both did a great job as a speaker, and thank you, audience, for joining. Then, as we have come to the end of the webinar, I thank each and everyone for giving their best on running the webinar online during this lockdown. And I hope that this webinar will be useful for you guys in the field of academics. Okay, thank you everyone. This is Nitish Kumar Katimani saying have a nice evening.
Our world is changing.
Engineering is changing.
Society is changing.
We are changing.
We're here to inspire,
inform,
influence,
and change perceptions.
Demonstrating how important engineers and technicians are in our lives.
championing achievements, helping to create new technologies that enable us to thrive,
and inspiring future generations to make a difference.
Together, we discover new concepts by turning theory into practice.
Create solutions to society's biggest challenges.
Share knowledge and expertise through our networks.
grow by developing new skills and capabilities,
Evolve and adapt for the future.
We are the IET.
Together, we are engineering a better world.